Yes, welcome you all for another an excellent presentation from Effective and Efficient Electronics for Excellence. In today's presentation, I would like to explain you about the basic applications of various transformations which are applicable in engineering applications. Normally, these are the various transforms normally an engineering graduate can able to study during his first and second year of engineering course under the engineering mathematics subject, right? So basically there are various transformations are available. Actually, in this presentation or in subsequent presentation, I would like to explain the various transformations, the various transformations, the various transformations that are applicable for our engineering applications point of view. Especially, these transformations can be applied in electronics communication as well as in electrical and electronics engineering, as well as in many other, especially in communications, in signal communications especially, right? So these transformations can be widely useful actually, right? So what are the various transformations available? Actually, what do you mean by a transformation, or what do you mean by transformation? Transformation is nothing but transforming a signal from one form to the another form actually, right? If you can easily understand this concept in this way, let us see, this is a transformer. Let us say this is a small box. I can call it as a transformer. So it has certain input actually, and it has corresponding output actually, right? This is output, right? So normally we can give our input as in the form of some signal. You can write x of t if it is a continuous signal, right? Or otherwise it can be a discrete one also. Most of the time we will discuss about the continuous time signal. That's why a continuous time signal can be, or a continuous time function otherwise can be denoted by the letter x of t. If you write the letter small t in the bracket, nothing but it indicates a continuous time function, or can also be called as a continuous time signal, right? Sometimes this continuous time function or the continuous time signal can be transformed into in another form. This can be converted or transformed into another form. It is required sometimes as per the application point of view. Therefore, we need the transformer. Therefore, we need transformer in such a way that this transformer will transform the input signal or the input function x of t to the corresponding output function. This is also function actually, right? That is what a basic transformation or the transformer meaning. Transformer or the transformation is nothing but transforming or converting, you can say, the information from one form to the another form basically, right? Okay, as far as our engineering mathematics, or otherwise as far as engineering application point of view, what are the various transformations are available? What are the various transformations are available? So as we are studying about the various engineering subjects from our electronics and communication branch regarding, as well as the same are applicable for our electrical and electronics and even electronics and instrumentation branch also. And for these three branch exclusively, there are certain common subjects we have, right? Therefore, normally in these groups or disciplines, we will discuss about two types of signals we will come across actually. Those are, one is a continuous time signal or a continuous time function, right? A continuous time signal a continuous time signal, or can also be called as a continuous time function, you can say, no problem, a continuous time function. And this is the first form actually, can be denoted as x of t, can be denoted as x of t. It is a continuous time signal, or sometimes can also be called as a function, right? This is what a continuous time signal or a continuous time function. And normally the another one is nothing but a discrete time actually. Second one is a discrete time, discrete time signal, a discrete time signal, or otherwise a discrete time function. You can write discrete time function. Okay, so this is denoted by x of n, x of n. Clear? So this is x of t. Wherever x of t is there, simply remember that it is a continuous time signal or function. Or otherwise, if you come across x of n, if it is given x of n, this is nothing but a discrete time, because discrete time is denoted by small n and a continuous time is denoted by small t. Remember that. That is the simple difference between a continuous time and then a discrete time. Discrete time is denoted by small n actually, and a continuous time is denoted by small t actually. That is the basic difference between these two. Well, now in order to study about the characteristics of a continuous time signal or otherwise a discrete time signal, or means that sometimes these continuous time signal or discrete time signals shall be transformed into another domain or into another function via certain transformations, with the help of certain transformations. So what are the transformations available? So in order to study about the continuous time signal, right? So this continuous time signal sometimes can be transformed into another domain, basically, that is nothing but frequency domain. Remember that. What is that? Frequency domain. In short, I can write FRQN. FRQ whole power n can be written actually, or otherwise you can write frequency FREQUNCY, right? Frequency domain. So sometimes the time domain signal can be converted into frequency domain. How it is possible? So this is possible with the help of the transformation. Okay, sometimes our x of t must be converted into frequency domain, or sometimes our x of n can be converted into frequency domain. How these can be converted? I think you are getting right. Now why? Because as far as our discipline is concerned, we need to discuss, we need to understand about the characteristics of the signal in time domain, how the signal can be estimated or how the signal can be defined in the time domain. And obviously the another domain is the frequency domain. Any signal can be studied in these two important domains actually, in time domain as well as frequency domain, right? Any signal or any function, you can say, no problem, any signal can be studied in time domain, and definitely in frequency domain also, in frequency domain, right? So time domain is nothing but, in time domain we will represent as x of t, and in the frequency domain this we will see actually. This is what I am going to discuss now. If this is continuous time, okay, if it is discrete time, it is x of n, and correspondingly how in the frequency domain how this x of n is represented or denoted, that we will see, right? Clear? So any signal can be studied into these two types of domains, frequency domain, a time domain, as well as the frequency domain, right? So here basically we have three types of important transformations are available, right? There are three important transformation. How many? Three types of three types of transformations are available actually. Three types of transformations are available. What are those? What are those? So in order to study the continuous time, this is what x of t is a continuous time actually. It is a continuous time, whereas x of n is a discrete time. So always remember this. This is discrete time actually. X of n is discrete time. This is a continuous time. To study about a continuous time, we will use Fourier transformation. Fourier, Fourier. Fourier transform. What is Fourier transforms? Fourier transform, right? Fourier is the scientist name actually who has invented this transform actually. So this is Fourier transform is the one first type of transformation, and the second one is Laplace. Second one is the Laplace transforms. Second one is the Laplace transformation or Fourier transformation or Laplace transformation. These two transformations are applicable for a continuous time signal. In order to study the characteristics of a continuous time signal or continuous time function, we will use Fourier transformation as well as the Laplace transformation. Clear? These two are the very important. And there is one more very important transformation is there, and that is used for discrete time signal. In order to study the nature or the characteristics of a discrete time signal, we will use the another type of transformation that is called Z transformation. What is that? That is Z transformation. So that's why. How many transformations are there? There are three transformations. The first one is Fourier transformation. The second one is the Laplace transformation. The third one is the Z transformation. Right? So as far as engineering graduates is concerned, normally you will cover these transformations during your mathematics course also, right? And afterwards the same will be you will cover in your subject core subjects also, like signal systems, like digital signal processing, is it not? So there you will use the applications of these transformations, especially in signals and systems, as well as not only that. So the Laplace transformations can be used in control systems also, and even networks and analysis subject also, right? In order to find out the transfer functions, right? In these applications, the Laplace transformation is widely useful. Clear? So therefore remember that these are the three very important transformations are applicable as far as our engineering mathematics is concerned, or even the same can be studied in your core subjects like signal systems, digital signal processing, like that, right? This is the basic brief introduction actually regarding the transformations. Understood? So in today's presentation, just I'm very much interested to bring your notice is that to know about the Laplace transformation. Laplace transformation, because it is widely useful transformation and very simple transformation to understand, even to apply to the signal. Afterwards, I will cover the remaining two, the Fourier transformation as well as the Z transformation, right? So let us see what is a Laplace transformation, how this transformation will be used for a continuous time signal, how a continuous time signal can be transformed into the another domain, right? So Laplace transformation, Laplace transformation. What is a Laplace transformation? Remember that this Laplace transformation, as just now I have explained, this is applicable for continuous time signal. Remember that. This is applicable for continuous time signals or continuous time functions. If you use this Laplace transformation in mathematics, there it can be called as a continuous time function, that is x of t or f of t, whatever it is. Whereas if the same Laplace transformation, if you are cover this particular in your core subjects, there we will call it as a signal, continuous time signal. That's it. Both are same otherwise, continuous time signal or continuous time function, whatever it is, right? And remember that this is applicable for a continuous time signal. And obviously, if it is a continuous time signal, normally the independent variable is a time actually, small t. The independent variable is a, what is the independent variable? The time. Time is an independent variable. And definitely how this time varies actually, that is very important, right? As this is applicable, as the Laplace transformation is applicable for a continuous time signal, continuous time, this time is independent. This time is independent. Time is t. This is independent. Of course, how this time varies actually from where to where? So this time varies from minus infinity to plus infinite. That you must remember. The time varies from minus infinity to plus infinite in time domain, okay. Okay, so this is about the Laplace transformation as it is applicable to a continuous time signal x of t, and here the time t is an independent variable that depends, okay, that varies from minus infinity to plus infinite. Clear? Now our aim is to transfer this x of t with the help of the Laplace transformation into the another domain actually. What is the domain? How it will be transformed, that we will see now. Clear? So remember that, say for example, this is, as I have explained just now, this is a Laplace transformer. You can call it as Laplace transformer. This is my x of t. This is what? This is input actually, and this is my output. And here, you know, it is after the application of this Laplace transformation, your x of t will be converted into x of s. Capital X of s means small x is converted into capital S, I mean capital X, and the small t will be converted into s. Remember that. So small x is converted into capital X and the t will be converted into s. In fact, here s is nothing but j omega. Remember that s is nothing but j omega. What is your omega? Angular frequency. What is this? Angular frequency. Angular frequency. So nothing but what actually? So your time domain is converted into frequency domain. If you write in place of s, you can write j omega also. J omega. Then definitely it is a frequency domain. Therefore, we are transforming the time domain signal into frequency domain signal with the help of the Laplace transformation. How this can be defined? So there is a beautiful definition for this x of t. So if x of t is a time domain signal where the time varies from minus infinity to plus infinity, okay, where the time varies from minus infinity to plus infinity, then according to this Laplace transformation, so I can write like this, the definition: Laplace L of t of x of t means the Laplace transformation of x of t, right? The Laplace LT of means Laplace transformation of x of t is nothing but, remember this, integral minus infinity to plus infinity e power minus s into small t into x of t, means this is what my input signal actually. That's why this x of t is nothing but my input signal, x of t into dt. This is what the definition actually. This is what, if you put in a bracket, this is what the definition of a Laplace transformation, right? This is what the definition of a Laplace transformation. Clear? So LT means means Laplace transformation of x of t. X of t is nothing but your input is equal to minus infinity to plus infinite e power minus st. This e power minus st is a very important parameter that plays very important role in transforming the time signal into frequency signal, where s is j omega. As I have explained here, your s is nothing but j omega. X of t is obviously your input signal. Therefore, this is the integral over minus infinity to plus infinity e power minus st into x of t into dt. And further, this whole is represented as your capital S x of s. This integral, everything will be denoted as capital X of s. Therefore, you can simply say that x of t converted as x of s. Your x of s is nothing but this integral. This is what a Laplace transformation. This is the integral, simple integral that can be used for transforming the time signal into frequency signal. Understood? And remember that here, as we are considering the interval of time, means we are integrating this particular function, I mean x of t, with respect to dt. Therefore, obviously your values minus infinity to plus infinity are nothing but the limits of time. Therefore, we are considering from minus infinity to plus infinity. So that's why this is called a bilateral Laplace transformation. This particular equation, you can call this as the equation number 1. This equation number 1 is called as a bilateral Laplace transformation, or also called as a two-sided Laplace transformation. This is called as because so we know that on a timeline, this is a timeline, so definitely 0 will be there in middle, and you can represent plus 1, plus 2, plus 3, plus 4, plus 5, and so on and so forth up to plus infinite. This is time axis actually. Let us say this is timeline. This is from 0 to, this is what on the positive side, plus infinity. Similarly, come to the left side, it is minus 1, minus 2, minus 3, minus 4, and so on and so forth. It goes to minus infinity actually. This is also time only. This is the negative part. So here in this particular integration, I am considering the total minus infinity to plus infinity, both sides. This is one side, 0 to plus infinite one side, and 0 to minus infinity, this is the another side actually. This is one side, this is the other side. Therefore, in this integral I am covering both sides actually. That's why this particular equation 1 is called as two-sided. What is the name for this? Two-sided Laplace transformation. You know, it is called two-sided Laplace transformation. Two-sided Laplace transformation, also called as bilateral Laplace transformation. Bilateral, because minus infinity to plus infinity we are considering. Therefore, that's why it is called as bilateral, or otherwise two-sided. Okay. In most of the cases, what we will consider is that 0 to plus infinity only. Most of the time, we will consider 0 to plus infinity only. In that case, this particular equation number 1 becomes as, in this particular equation becomes as 0 to plus infinity only. So, I can erase these limitations. I can put 0 to plus infinite. I can change 0 to plus infinity only. Then in this case, then you can write this equation number 2. In this case, you can write this as equation number 2. Now in this case, actually now it is the limitations, the time limits are changed now. We are considering 0 to infinity, means only one side we are considering. That's why this particular equation number 2, now this is called equation number 2. This is called as one-sided instead of two-sided. This is called one-sided. This is called one-sided Laplace transformation, or also called as unilateral. What you know? Unilateral Laplace transformation. So most of the time we will use this particular definition only, this particular definition only. Most of the time we will use unilateral only. This is the simple integral we will use in the transforming the in the Laplace transformation. Okay, in the transforming the input signal into frequency domain. I think you understood this, right? And just for your understanding, I will explain you a simple example actually how the time domain signal is converted into. I will explain with a small example that is very beautiful example. Let us say if my x of t is, let us say my x of t is u of t. Let us say for example, let x of t is equal to u of t, where u of t is a unit step function. What is this? Unit step function. And find the Laplace transformation. Then find Laplace transformation of x of t. This is nothing but Laplace transformation of u of t. Clear? What is the answer for this? So, to solve this particular problem, you must know the definition of what is u of t, right? I am writing the solution part of it. Clear? So, what is u of t? We know that a unit step function is defined as unit step function. What is a unit step function? It is denoted by u of t, and u of t is equal to 1 actually for t is greater than or equal to 0, and it is 0 for t less than 0. Clear? This is what the definition of a unit step function means, that the unit step function is 1 for t is greater than 0. If you represent this, I think you already know this. This is something like this. So this is 0. This is time actually. This is time t, and this y-axis is nothing but your u of t, unit step function. The function normally will be denoted on the y-axis, and the time will be taken on the x-axis. And for t is greater than 0 means that what? So 0 to infinite, the limit is 0 to up to plus infinite. So for all the values 0 to infinity, the value remains 1. 1 nothing but somewhere here. So means that what? At 0 it is 1, at 1 it is 1, 2 also 1, at 3 also 1, up to infinite. If you add all these points, then your signal will be like this. This will goes up to infinity only. And for this portion, what is this actually? T is less than 0 means less than 0 is nothing but this portion left side. So for this your signal will be 0, therefore no signal here, 0. Therefore this is what your signal, 1. This is the thing. Therefore this is the definition of a unit step function. Unit step function 1 for t is greater than 0, and it is 0. Therefore this is not required now. This is useless information. This is what the very important information, right? Now if you apply these limitations in that Laplace transformation, then I am erasing this, but I will solve this for you, right? So you must know the definition of a Laplace transformation, right? What is the definition of a Laplace transformation? So we know that LT of x of t is equal to LT of u of t, means unit step function x of t is nothing but u of t. What is the definition actually? It is minus infinity, general definition, minus infinity to plus infinity, e power minus s into t into x of t, not it is x of t dt. Clear? This is general definition. But what is our x of t? It is u of t. What is u of t? Write this. So actually u of t is nothing but your, means that what? So write this, minus infinity to plus infinity, e power minus st, right? So your x of t is nothing but, in x of t you write u of t and dt, right? Right? So in place of x of t you write u of t. So what is u of t? U of t is a unit step function. So what is unit step function? It is 1 for 0 to infinity. Therefore you write in next step, this is 0 to infinity e power minus s into t. In these limitations, what is u of t value? It is 1. Therefore into 1 into dt. Clear? This is simple integral. Now you evaluate that, then definitely that is nothing but 0 to infinite e power minus s into t into dt. That's it, no? E power minus st into 1 is nothing but e power minus st dt. Now if you take the integral integral of e power minus st. E power minus st is nothing but e power minus st by, so we are integrating with respect to time, therefore minus s will come in the denominator. In this particular, apply the 0 to infinity limitations in this. Wherever t is there, you substitute upper limit infinity and lower limit 0. This further, this is 1 by 1 minus s, means minus 1 by s you can take outside actually, then put bracket here, then e power minus s into t is there. In this, substitute 0 to plus infinity, right? Then if you substitute that, what you will get? What is the next step? What will be the next step? So definitely, so this is something 0 to infinity e power minus st into dt is equal to this final actually minus 1 by s, you will keep here bracket, in place of t substitute infinite, means e power minus s into infinite minus, because for applying upper limit as it is we will write that, but for this lower limit minus will come, so minus into e power minus s into 0. This is what, this is how you need to apply the limitations. Again it is 1 by s actually in bracket e power minus s into infinity, so s into infinity is infinity, infinity into minus, it is minus infinity, and it is e power 0 into something 0, 0 into minus 0, something is 0. This is equal to minus 1 by s, it is e power minus infinity is 0, e power 0 is 1. This is equal to 0 minus 1 is minus 1, minus 1 into 1 by s, 1 by s your answer. So your answer is 1 by s. That is what your answer. Clear? That is what your answer. Therefore, what is the answer actually now? Tell me. Therefore, for the signal x of t, nothing but your u of t. Okay, the Laplace transformation of x of t, or this is equal to Laplace transformation of u of t, that is nothing but, it is nothing but 1 by s. This is what the answer. Means that what? U of t is nothing but, u of t is transformed as Laplace transformation, it is 1 by s. This is how you can write. U of t is equal to u of t, the time function is unit step function. After application of Laplace transformation, it converted as 1 by s. So time domain, converted into s domain. So in the output, means in the result after the transformation, you will get your answer in terms of s only. S only will get in the terms of s only, right? This is the basic information that I wanted to explain you in this presentation, and with the detailed information we will see in the next presentation, right? I hope you understood well, and I like to request you all to share to your friends, and you can comment or you can give your feedbacks and suggestions to improve this particular channel, as well as it will be good for you to improve this, right? So with this, we will finish off today's presentation and continue the next presentation. Have a good day.